Today we are going to discuss on a very important topic about the grouting and which has a tremendous impact on thermal impact restoration. So let's start with the core problem this presentation addresses. Thermal decoupling in the blast furnace hearth is a very alarming thing that happens in the furnace. This image on the screen shows a simplified cross section. The bright blue lines represent the intended cooling path. The orange rupture at the bottom indicate where that path breaks down. Our objective is straightforward. Restore continuous thermal contact. Without it, the hearth cannot maintain its protective freezing line and shell life is compromised. To understand why decoupling is so dangerous, we first need to revisit how freeze lining is supposed to work. The freeze lining philosophy. Let us discuss on this. The freeze lining is not a coating. It's the result of successful heat extraction and we can say efficient heat extraction. As shown here, liquid iron freeze against the hot face of the refractory, forming an insulating protective layer. Now that layer stays stable only as long as heat is continuous pulled through the lining and into the shell cooling system also. This also signify the stability, consistency of the cooling and refractory integrity. Now every material layer in between refractory, grout, graphite and shell must remain in full mechanical contact. Now if any layer separate, the thermal chain breaks and freeze lining melt. And this is how the localized heat loads keep on concentrating on a localized area which are detrimental for the further extension of life of the furnace. So in this slide we can visualize that separation is what we call decoupling and it happens with the gaps smaller than most people realize. So look at the two states side by side. On the left, a healthy thermal breeze. Heat flows smoothly from the hot phase to cooling shell. On the right, a failed state. A air gap of just 0.1 millimeter exists between refractory and the shell. That microscopic void acts as an insulator. Heat cannot go longer to escape from this interface. The internal lining temperature spikes and the protective skull melts. Now this is not a slow degradation. Once decoupling begins, failure accelerates rapidly. So let me show you exactly what a 0.1 millimeter gap does to heat transfer mathematically. The mathematical threat of 0.1 millimeter void as it's shown in the slide. This graph plots heat flux against gap size. At full contact we see over 110 kilowatt per meter square of heat extraction. As the gap opens to just 0.1 millimeter, that value drops below 80 kilowatt per meter square. The critical threshold is 50 kilowatt per meter square. Below that line, the protective skull cannot sustain. It will melt. The refractory begins to degrade from the inside out due to this loss of skull and there is no safety margin here. Even a hairline gap pushes the heart towards the failure. That is why we intervene not with guesswork but with precision, grouting design for two specific goals. The dual mandate of the precision grouting is like this. The precision grouting serves two independent functions as we have discussed just now. First, the thermal restoration. We establish the high conductivity path to drop internal lining temperature and allow the frizz layer to rebuild. So this is one of the very important aspect, and this is how the further refractory gets blanketed with the help of this freezing line. Second is the gas sealing. The ward smear taffel allow high pressure gas to track through the lining. That causes splashing, spitting, unsafe casting condition, a lot of wear tear in the main trough, life of main trough also decreasing, and above all, a lot of emission. Sealing those voids eliminate the gas path entirely. Both goals must be achieved in every intervention. But before we can grout, we have to locate the void, and that requires the right diagnostic tool. Now coming to the diagnostic framework, locating the void, the thermocouple shown in the top box give us point measurement. They are reliable but blind to anything not directly adjacent. To see the full picture, we use impact echo acoustic mapping. This method sends pressure waves through the shell and read the return signal. It works like sonar for refractory lining. The result, we can identify, locate and quantify decoupling across the entire hearth cell, whether the furnace is on blast or off blast. So here is what that data looks like in practice. So coming to the validation of the diagnostic strike zone, this is an actual acoustic map of a hearth shell. The orange circles are impact echo measurement clusters. Each one represents a location where decoupling was detected. The cyan allows indicate or planned grouting injection points. We do not drill randomly. The acoustic map tells us exactly where to intervene, how deep to go, and how much material to inject. This is targeted, data driven maintenance. And this is going to be only more fruitful when we have got a very holistic view of the gaps. So once the void is located, we must select the correct grout. Temperature dictates the choice in this. So selecting the right mix for this grouting is also very important. So grout selection is not optional, it is temperature driven. So for high temperature zones above 200 degrees centigrade such as ramming joint, we use a tar or resin based grout. It requires preheating to 60 degrees centigrade to achieve injectable viscosity and sets rapidly above 200 degrees centigrade. Silicon carbide or graphite grains must be added to ensure thermal conductivity. For cooler boundary zones below 100 degrees centigrade, specifically the shell to graphite interface, we use a cement bonded alumina grout. It requires minimal water content, that is 15% by weight, and deliver thermal conductivity up to 3. Uh, so it's also a water insoluble and stable to 400 degrees centigrade. Now using the wrong grout in the wrong zone guarantee the failure. So we do not rely on theory. We validated the flow behavior experimentally. Now coming to the empirical validation of the fluid dynamics, this simulation used the steel and plexiglass assembly to replicate the shell to refractory gap. We pressurize the grout into a narrow interstitial space and monitor flow behavior in real time. Let us discuss on the result. The material is spread completely into ultra-narrow void fills without shagging and harden in place. This is empirical proof that the restored thermal bridge is permanent. Now let's walk through the actual field of execution protocol. Step 1. Weld injection socket to the hearth shell and drill 12 mm access hole. Monitor shell temperature with an infrared device. Keep it below 150 degrees centigrade during local cooling stops. Step 2. Verify the void. Insert a physical hook to confirm decoupling. If multiple sockets are installed, inject pressurized air to check for interconnected pathways. Step 3. Precision injection. Place the grout pump on a calibrated scale. Inject at low pressure 3 to 5 bar. Stop only when the injected weight stabilizes, indicating the void is full. Step 4 is about the seal and lock off each valves. Permanent sealing is required before returning to the blast pressure to prevent gas escape. So, does this method work? The data from an actual field installation answer that questions. This chart shows heat flow over time. The white line tracks heat extraction before grouting, low and very unstable. The CN vertical line marks the grouting intervention. Immediately afterward, the red line shows a sharp sustained step increase in the heat flow. Higher heat flow at the same graphite temperature means only one thing: thermal contact has been restored. The cooling system is work again. So restoration is not the final step. Post-care sealing is also equally critical. Post-care and sealing, as these are very critical, every drilled hole is a potential leak path. If left unsealed, high pressure gas will track through the socket, causing oxidation of the safety graphite layer. That oxidation destroys the lining from the outside in. Independent of thermal condition, the diagram on the right shows a correctly sealed socket with a plug blocking gas escape. This is not optional. Sealing is part of the intervention, not an afterthought. To summarize, decoupling is inevitable, but failure is not. The This blue loop represent the new standard of hearth management. Monitor for decoupling using acoustic mapping. Select the correct grout for the temperature zone. Execute precision injection with weight-based confirmation. Validate thermal restoration via heat flow data. Decoupling will happen. Thermal expansion and shell movement guarantee it. But with precision grouting, that inevitably becomes a manageable maintenance event rather than a catastrophic failure.